Hi, everybody. Today we're going to do well, obviously 3.8, and this is part video. This is our second video on this topic of differential equations. And today we're going to look at a very special type of differential equations, and it's called a separable. And let me spell that, SEP, separable. A separable differential equation. And basically, a separable differential equation is going to look something like this. It's going to be something like y prime is equal to f of x times g of y, something like that. Now, I'm just going to tell you this kind of in theory, then we're going to do some actual examples. It'll make a lot more sense. You see, y prime, I could write that as dy dx, and that equals f of x times g of y. And now what I could do is I could sort of cross multiply, if you will, and I could say 1 over g of y times dy equals f of x dx. And now I can integrate both sides. And now, of course, that's assuming that f of x is a function I could differentiate, I'm able to find the integral. Of course, that helps a lot. And if 1 over g of y is a function where I'm able to find the integral, that obviously you want to have that. But a lot of times it will be, and it'll make things, it'll be a much easier way to solve the differential equation. So let me give you an example. All this will make a lot more sense, I believe, once we have an example. So let me give you one right now. Okay, here's an example. Y prime equals 6x plus 1 over 2y. Now, this becomes, again, for separable differential equations, it's actually a little bit easier if you write dy dx equals 6x plus 1 over 2y. And I'm going to sort of cross multiply, and I'm going to get y dy equals 6x plus 1 over 2 dx. Notice I left the 2. I could have brought the 2 over with the y, but I chose to leave it here. That's kind of the way I've been trained to do it. Have only a y here and nothing else, but it doesn't really matter. We get the same answer either way. Now what I'm going to do is once I have this, I can now integrate both sides. So let's go right up here. The integral of y dy is equal to the integral, now I may as well bring the half out here, of 6x plus 1 dx. And now I just solved this. Each one is an integral. Now this integral, I'm going to write y squared over 2. Now I'm going to write, instead of writing plus c, I'm going to write plus c1. And here I'm going to write 1/2. Well, what is this? This is 6x. The integral of 6x is 6x squared over 2, which is 3x squared. And the integral of 1 is x. And then, of course, plus c, but I'm going to write c2. And what I want to do, usually I don't even bother writing the c1, because usually what I would do is if you subtract c1 from each side, so you get y squared over 2 equals 1/2 times 3x squared. There should be is there a plus? I didn't write the plus. Plus x. And I'm just going to call this whole thing c. There's c2 minus c1. It's just a constant minus another constant is still just a constant. So I'm just going to write a plus c. So usually what I do usually when we write, and you'll see I'll do more examples, I'm usually not going to bother writing c1, c2. I'm just going to not bother with this any kind of c over here and just put my plus c on the other side, and it's going to work out fine. Anyways, oh, you know something, now that 2 would have helped me, I'm thinking, but that's okay. So I'm going to multiply both sides by 2. That's my first order of business. Now, I can multiply the constant by 2, but multiplying a constant by 2 is nothing because it's just another constant. So I'm just going to leave it. They say that the way we say it in math talk is that if I multiply by 2, the 2 gets absorbed in the constant. And this becomes y squared equals 3x squared plus x plus c. Now let's so everybody, we have now solved. I like making a little fluffy cloud here. I don't know why I think it's horrible. We now have solved the differential equation. Now, what does it mean we solved the differential equation? It means I no longer have any y primes. I have x's and y's, but no y primes. So you have a y squared. That's not a y prime. It's a plain y squared, 3x squared, x, c. All that is good. I'd like to graph this. I'm gonna go to Desmos now, and I'm going to let's see. Let me go to Desmos and let me share my let me just come back here and share my screen with you. I'm sharing my screen, and here we go. And so we're gonna graph y squared equals 3x squared plus x plus c. And I'm going to add a slider for c. Okay, so let c equals 0. So if c is 0, this is what it looks like. This is what this looks like. It's kind of, notice that these lines here are kind of straight, and it kind of gets curvy over there. It's kind of cute. And let's see what happens. I'm going to let c move around. If c moves, look what happens to this. That's kind of awesome. That's kind of awesome. So when c, essentially when c is 0, that's very awesome. Let's let it move. I'm just gonna set it to go back. So when I notice that when c is positive, oh, and it switches when it's negative. When c is positive, you have a happy face and a smiley face. And then I'm sorry, when c is negative, you have a happy face and a frowny face. When c is positive, you have two. I'm sorry, positive gives me happy frowny, and when c is negative, I have a two side by side, left right faces. That's kind of very. This is a very beautiful function. Now notice each different value of c is going to give me a different function. So this is all I want to show you for the moment. So let's just stop it here. Let's go. Let's stop at c equals 0, and c is 0. Come on, c be 0. Okay, so I'm just going to stop it just for the moment when c equals 0. Notice that when c equals 0, our curve passes through the origin, which makes sense because if c is 0 and x is 0 and y is 0, I just get 0 equals 0. That's kind of interesting how it passes, hits the origin right there, and and that looks like negative 1/3. How interesting. When c is 0. Anyway, let's go. I want to do another problem. I want to do something called an initial value problem. So I'm going to go to the next. I'm going to need another page now. Now what I'm going to do is I'm going to write the same exact equation that we just had. I'm gonna do the same exact equation that we just had a minute ago. Only this time um, I'm going to add that what we in the business call that initial value. So let me just write that right here. Okay, already. So I'm going to write an example here. So the example is y prime equals 6x plus 1 over 2. And I'm also adding in the initial value that y of 2 equals 3. So I have all that here. And this is called an IVP, initial value problem. initial value problem. There we go. Now let's solve this. Let's solve this and we'll have some fun. So we are going to, we're over here. Well, really, by the way, I want to solve this. I could just go straight to the answer because we already figured out the answer, but I want to show you a point that there was a, as I recall, that was a 2y, wasn't it? It was a 2y. Sorry about that. I left out that y. So what I'm going to do is I want to do it slightly differently, just show you. Remember I said I could have brought the 2 over, but I didn't. Let's just see what happens if I would have brought the 2 over. So I would get 2y dy equals 6x plus 1 dx. Now I integrate both sides. And now this just becomes y squared. Again, I'm not going to bother with the C1, C2. I'll just put it, we just put the C at the end. This 6x becomes 3x squared. 1 becomes x plus c. And now, pow, I got, and that's the same answer I got, the same final answer I got before. I just realized I should stop sharing so I think you can see better this way. So this is what I did. In other words, this time I did bring the 2 over up on top. When I integrated, I got just plain y squared. So basically got rid of all the fractions, but it didn't change the answer. It's the same answer we got before. It was actually a little bit, actually wound up being a little bit easier because instead of having fractions and then getting rid of the fractions, I didn't have them to begin with. Anyway, now we want to do the initial value part. So y of 2, this means when x is equal to 2, y is going to equal 3. So I'm going to write here, and why am I doing this? Because I want to solve for c. So y squared equal, I'm sorry, whoopsie, 3 squared, let me start all again. 3 squared equals 3 times 2 squared plus 2 plus c. So that's 9 equals, what's that, 12 plus 2 plus c, which is a 14. So -5 equals c. So my solution now to the IVP, the initial value problem, is specifically y squared equals 3x squared plus x minus 5. And this is my IVP, initial value solution. My initial value. This is a solution to the specific case. In other words, before, when we got a plus c, that was a general case. That gave us what we call a family of functions. Now we have the specific function where y of 2, which passes to the point, basically, which passes to the point 2 comma 3. So let's go back to Desmos. Let me share my screen again. Go back to Desmos. And I'm going to put in c equals -5. C equals -5, which is right there. And I want to look at the point 2 comma 3. Well, you could see it's that guy right there. That's 2 comma 3. But we can just check that out. We can just type in the ordered pair 2 comma 3, 2 comma 3, and we can even label it. And there we go. So we see that our equation, our differential equation, the curve. Now, this is the only differential equation that passes to that point. That's kind of cool. So that's quite remarkable. Yes, quite remarkable. And there you go. That is our solution. I wanted to make what just happened here? I wanted to make a point. For our initial value problem, I'm not saying you have to, we're done. We have our solution. We're happy. Everything is good. Sometimes we want an explicit y. So sometimes, not necessarily all the time, but sometimes, and that would depend on the problem or the situation. We want an explicit y, meaning to say not y squared equals, but y equals. So if I just square root each side, I get y is equal to the square root of 3x squared plus x minus 5. Now, hold on. There's a little bit of an ambiguity here because really, when I take the square root of each side, this could be the plus or minus. Y could be the positive square root. And then when I square it, I get this guy right here. Or y could be the negative square root. And when I square it, I still get that whole guy right there. That whole guy right there. So, I thought I was making things better. It looks like I'm making things worse. Well, in general, I wouldn't know. It could be the plus, it could be the minus. However, here we have a clue because since we know it goes to the point 2 comma 3, that tells me that the y values are going to be all positive. That tells you the y. See, because that's y of 2, so that tells me we're looking at the positive square root. So therefore, the explicit solution would be y equals positive square root of 3x squared plus x minus 5. And that is our beautiful, and that is fantastic. But wait a minute. Let's go back to Desmos and check this out. So I have y equals the positive square root, because we said that y is positive. This might be very, very informative here. So we're gonna go back and to Desmos. So I gotta share my screen. I gotta share my screen again. Sorry about that. I gotta share my screen again. I'm not sorry about sharing my screen, but I just want to share my screen. And now we're back to Desmos. We'll look at this. We said that y has to be positive. We said that y has to be positive, but I have a problem. I have a problem with positive because now what this is saying here, so we just said that if it's a positive square root, that means we're going to have positive y values, which means it's only the top half. It's only the top half of this graph. So is this now that actually makes a lot of sense because if I have let's look at the right side. If I have the top half and I also have the bottom half, then I fail the vertical line test. So in order for it to be a function, I could have the top or the bottom, but not both. So it's either really if it's the positive square root, it's going to wind up being both tops. If it's a negative square root, it's going to be both bottoms. But they're both going to be strict functions that pass the vertical line test. So it's actually going to be very, very good. That's actually going to work out beautifully. Wow, that's fabulous. Let's look at another example. Let's look at another example. What dy dx is another example. Dy dx is equal to x squared over y squared. So this becomes, we just kind of cross multiply, we get y squared dy equals x squared dx. I'm going to integrate both sides, and I get y cubed over 3 equals x cubed over 3 plus c. Now I'm going to multiply everything by 3 on both sides. I'm going to multiply everything on both sides by 3. And I get y cubed equals x cubed plus c. Now, the 3 times the y cubed over 3, so the bottom 3 cancels. This 3 cancels out that bottom 3. But how come 3 times c? Shouldn't that be 3c? The answer is yeah, but this is another case of the constant getting absorbed into the c, because 3c, c is a constant. 3c is a random. C is a random constant. 3c is a random constant. It's just so this is my solution right here. And let's graph this on good old Desmos. So I'm gonna go to let's get Desmos here. Let's get up Desmos. Here we go. Sharing my screen with you. And let's we don't need all these. So let's graph y cubed equals x cubed. Okay. Plus c. I'm gonna add a little slider. Oh, that's a very interesting curve we got there. Very, very interesting curve. And let's see what happens when C. Oh, look at that. When I make C bigger, the bump gets bigger. It's a big, big bump. Now when I make C, when C is 0, now essentially when C is 0, it's get a straight line. Because of Y, oops, not the 0. Stop at 0. 0, stop. When C is 0, it's get a straight line. Which makes sense, because Y cubed equals X cubed means Y equals X. So it's just a straight line. And once C becomes negative, the bump goes the other. Oh, actually, let me let this thing run. So the bump is, so it's just going to be a bumpy bump. And of course, if I had different, and these all represent different values. Every one of these curves is part of that, family of functions. That's so fascinating. Okay, let's, you know what? Let's, as long as we're having fun here, just looking at here. That is very interesting. Okay, so let's, okay, I gotta stop there because it's getting me dizzy already. And let's do a, let's take this and turn it into an IVP. So suppose I have the same problem, but I want to pass to the point. I want that y of 1 is equal to 7. Y, oh sorry, y of 1 equals 2. My bad. Y of 1 equals 2. Another way of saying that is that I want it to pass through the point 2 comma 1. That's another way to say that it passes through the point 2 comma 1, or to say that y of 1 equals 2. That's this and this are two ways of saying the same thing. Well, anyway, I'm just going to plug in y equals 2 and x equals 1. So 2 cubed equals 1 cubed plus c. And my goal is to solve for c. So I want this specific particular function that passes to this point. Because as we saw, there are a lot of functions as c roams around. I want to find which c value is going to make this happen. Well, that's 8 equals 1 plus c. And then, of course, that gives us c equals 7. That's why I made a Freudian slip here. I wrote 7. I said 7 because I knew that was going to be the ultimate answer. So, and 7, the number 7 was on my brain. Anyway, the answer now to the IVP is y cubed equals x cubed plus 7. And that's going to, and there you go. That's make that 7 a little more clear. That's at 7. Sometimes I notice that when I try to make something better, ones that make it worse. That's a big giant 7. Now it looks like some ugly creature, but it's y cubed is 7. Hey, let's go to Desmos. Let's go to Desmos and graph this. Okay, so we're gonna share the screen, and here we are. I want to look at the point. Let's see, as I said, 2 comma 1, 2 comma 1, and let's even label it. So there's 2 comma 1 right there, and I want to set c equal to 7. That's very weird. Desmos is not being cooperative here. So why would that be? Now, why would that be? Why would c is equal to 7? Isn't that strange? Isn't that strange that c is equal to 7, and yet it didn't bear out y cubed was 2 cubed. That is so bizarre. Why would that be happening? Isn't that bizarre? That should not be happening. Looks like we have a dilemma here. I wonder how we could figure that out. Let's think about this for a second. Let us put on thinking caps. Okay, so you had enough time to think about it. Did anybody figure out what went wrong? A very simple, a very, very, very simple thing went wrong, and we're gonna get a lesson from this. I said that y of 1 equals 2, and then I wrote here passes to the point 2 comma 1. But you see, the y value is 2 and the x value is 1, so it actually passes to the point 1 comma 2. And Now, once we make that change from 2 comma 1 to 1 comma 2, you see that? Because that's x is 1, y is 2, so I just wrote it backwards there. And once I make that change, this is everything is so now here we have x is 1 and y is 2. That's all beautiful. Nothing's going to change. My answer is still going to be c equals 7 because here everything was plugged in the right way. 1 got plugged in for x and 2 got plugged in for y, so everything worked out right. It's just that when I wrote the point here, I just wrote it the wrong way. So, and that's the beautiful thing about math. You could check. I love when you do something and then you see it doesn't work out. You could go back and find the step where it worked, and I love that. So let's go right back here where it was. Let's go right back to Desmos. And all I'm gonna do is I'm gonna change the point here to 1 comma 2, 1 comma 2, and I'm gonna leap and we're done. And look at that. Once I change the point to 1 comma 2, it all works. You see the curve that we got fit through, and it's all beautiful. And that is very heartwarming. Indeed, that is heartwarming. That was okay. Let's stop the share. Well, it's been loads of fun. I'm gonna stop this video now. I am gonna continue with the part 3. We're gonna do some business applications of this concept of separable differential equations, and that's gonna be on the next video. Anyway, for now, it's been loads of fun, and we'll see you guys next time. Bye.